Thank you, and thank you very much for the invitation, for being here. It was really a great pleasure to be here, and it still is. So I'll give an overview talk, mostly. So several of the work has been done not by me, but by students from Utrecht. Our overview talk on tree decompositions, tree width, and algorithms on these, which exploit dynamic programming and recent techniques how to make these algorithms faster. So I'll first talk about tree width and tree decompositions and explain a concept which is called nice tree decompositions, a special type of tree decompositions. Old theory, how you would do dynamic programming and solve dominating set problem as a typical example. And then I'll talk about two techniques which recently were made to speed it up. And I'll start with the notion of convolution, or basically a transformation of the base or of the representation of something to speed this up. And then a very new technique which was by 6 authors now in the coming Fox paper, and I'm not one of them, but 2 of them are my students, so I'm still proud of that actually. And I'll give as example here the Hamiltonian Circuit problem. There are many corollaries and I'll have some conclusions at the end. So first, tree width. So tree width is a parameter on graphs which tells more or less how tree-like a graph is, and I'll define it more closely later. So the first introduction of tree width appears in the work of Robertson and Seymour on their fundamental work on graph minors. But actually the notion was predated by other notions like partial K-trees and some others earlier. The reason why tree width is interesting is for several reasons, not only because of its role in the graph minor theory, but also because it makes intractable problems often easier when you restrict them to graphs of bounded tree width. And well, I'm a computer scientist, so I really like to look at algorithms and see how fast they are for solving problems, and this really has lots of applications, and I'll mention one later. So what is tree width? How do you define tree width? It's defined in terms of a structure which is called a tree decomposition. So if I have a graph, I associate to the graph a certain structure which is called a tree decomposition, and it should have certain properties. 3 properties. Every vertex should belong in at least one bag. So you have a tree, and for every node of the tree you associate a set of vertices. You can see vertices appear more than one bag often. For every vertex is somewhere. For every edge there is a bag containing both endpoints. For instance, the edge GF, you see that both G and F are here. This is true for every edge. And all bags containing the same vertex form a connected subtree. So for instance, all bags containing C are here. There is always a trivial tree decomposition of one bag containing all the vertices, but this is boring and you don't have, not very useful. So what you actually want is that these bags are small. And the tree width of a tree decomposition is the size of the largest bag, and then in the definition you subtract 1 for getting tree width 1. So this is the notion of tree width as being used in many papers. I'll give another equivalent definition you can see from the notion of nice tree decompositions later, and there are several others which are also equivalent to this one. So one way tree width is used is in algorithms that exploit tree decompositions. And many problems which are hard on arbitrary graphs, you have an algorithm which is linear or sometimes polynomial time if you restrict them to graphs of small tree width. And most of these algorithms have the following structure. There are 2 steps. The first step is I find some tree decomposition of width bounded by some small, say, constant k. And the second step is I use dynamic programming bottom up on a tree. Now for step 1 in practice you would run there are quite good heuristics who do this in practice. In theory you can do this for every fixed k in linear time, actually this is quite a nasty K, and in practice it's not so useful, but in theory it's very useful. And then there is for tree with 2, 3, and 4, there are fast linear time algorithms which have nice constants here. You can sometimes also construct these. For instance, for trees or series parallel graphs, you know that the tree width is 1 or 2, and you just construct your tree decomposition, and there are many other things. I'll mention some other results here also later. And then for dynamic programming, there has been really a lot of papers which use this technique and exploit this for quite a lot of problems, and this is where my talk will focus on this time in this talk, on how you can speed this up. So I assume your tree decomposition is given either by construction or as part of your input or whatever. I went one too fast. So many famous graph problems are of this form, that you have a linear time algorithm when you restrict your input to graphs of bounded tree width. There's also some practical applications. I'll mention one in my next slide. And this generalizes also many results for special cases like trees, forests, series parallel graphs, outer planar graphs. There you have algorithms for these, and these are just generalized in this way. You can also use this for other special classes of graphs, for instance planar graphs. Oh, these should be a square root of n, there's a mistake. So planar graphs have tree width order the square root of n. It's basically the planar separator theorem. So you have algorithms usually which run in time which is only exponential in the square root of the number of vertices in the graph instead of in the number of vertices in the graph. Graphs of degree 3 have tree width basically n divided by 6, so that also can help to speed up and to get some fast algorithms. And I'll give an example of that, use of this one later in the talk. So here is another example. These are probabilistic networks. These come from decision support systems. So you have decision support systems where people make a graph, and every vertex in the graph models some statistical variable. Well, this is of quite a nasty disease actually, and every variable tells a certain symptom of the patient or the stage of the disease in the patient. And how people use this is that actually for every vertex in the graph you have a probability distribution of that vertex given the ancestors, the direct ancestors of this vertex in this graph. And then they want to solve problems like, given certain values, what is the probability distribution for another value? And this problem is sharply complete, but in practice what they do is they notice that the tree width of these graphs happen to be in most practical cases small, something like 6 to 12, and then you can use some kind of statistical flavored dynamic programming algorithm, which is called the Lauritz and Spiegelhalter algorithm, and then they solve this problem. So this is, you can actually download programs or buy from the web. There are freeware versions and there are commercial versions where you pay thousands of dollars, and somewhere hidden inside these programs there's always an algorithm which computes the tree decomposition of the graph and exploits it. So there are different ways of showing that a problem can be solved in linear time if your graph is tree width. I think there are two important techniques. One is show that your problem fits in some framework, and the most commonly used one is the framework pioneered by Courcelle, monadic second order logic or extensions of it. And the other is to make the algorithm yourself. Of course, this gives in practice better algorithms with nicer running times. Of course, it's also usually much more work. And what I also did to describe these, it's handy to have so-called nice tree decompositions. So monadic second order logic, so is a language in which you describe graph problems, and you can have lots of constructs like for all sets of vertices, or there is a set of vertices, or for all sets of edges. And then you can write things like vertex V is a set NR of W, and you can use logical operations, and you can say that two vertices are adjacent, and so on. So there are a number of these things, and you can express, if you can express your problem in this language, then you can use Courcell's theorem that tells you that there is a linear time algorithm for this problem in graphs of bounded tree width. And there are extensions for optimization problems. So for instance, you can find the minimum set of set of vertices such that a certain property holds. Once you get the hang of this, it's a very powerful method, because it's basically like a programming language. Also, you have properties which run like a subroutine. So if you know that you can write this set induces a connected subgraph, then you can use that later, and so on. And if you know this, it's very easy to see in this way that for many problems that they actually can be solved in linear time. Now let's go to nice tree decompositions. Now these are a special type of tree decompositions where I assume my tree is rooted, and I have 4 types of nodes: leaves, joins, introduce, and forgets. And I'll show them later what they actually are doing. And there's always a nice tree decomposition with the same width, and you can actually transform a tree decomposition to a nice one in basically linear time times a polynomial in the width. That's not so hard to do. But so let's see what these do. I have 4 types of nodes. Now a leaf node is just, I'm pressing the wrong button again, and I have to point it here. So, what I also do is for every node in my tree decomposition, I associate to it a certain subgraph. And the idea is I take all the banks in the nodes which are below that node, all these banks together, and then the edges between these vertices. And what happens in the nodes that basically, so if you have a leaf node, then a leaf node is just a node with just a bank containing of one vertex, and then the subgraph corresponding to it is just a single vertex. So a join node, what you have is you have a bank with two children, and they have the same vertices. And the join, what you do is in the join you take these 2 subgraphs and you identify these border vertices. So in this way, so you get basically this graph from this. So this is a join. You have this here. This is a join node. An introduce node is what an introduce node is, but I have a node and I just add one new vertex to it, and this new vertex can have only neighbors in it can only have neighbors in this boundary. So you add a new boundary vertex. This is what and this new vertex cannot have edges to these vertices, which are not anymore in the boundary. And then the last one is where's the last one? Introduce, join, forget. The forget is forgotten. Oh, it's just one sheet too far away. It went to the next section actually. So for the forget node, what I do is I take one boundary vertex and it's now a normal vertex. So I basically decrease the boundary. So my graph doesn't change, just the boundary changes. And so basically what you have is a nice tree decomposition, kind of a parse tree. It gives you the tree, and just the size of a boundary is more or less the tree width, minus you have the -1 there. So you have these operations which make larger graphs, and if you can make the graph with these operations with boundaries of size k, then the tree width is k-1. This is another way of defining tree width. And what you do in the dynamic programming algorithm is you describe some information about your graph, but in terms of what happens in the boundary, because these vertices here, they're interesting but less interesting than these, because these vertices will never get new neighbors. So basically this boundary works as a separator. It separates the already forgotten vertices from the rest of your graph. And this is the way this works. So let's see what I had to now come to section 3, the dynamic programming, and then I look to the dominating set algorithm. So what I do for dominating set is I want to make a dynamic programming algorithm on graphs of say 3 with k for dominating set. Now what I do is I basically I say, let's suppose I have a dominating set in my entire graph. What happens if I take a subgraph with a boundary?
Can you explain the dominating set?
Dominating set problem. Okay, sorry. So a dominating set is a set of vertices such that for every vertex it's either in the dominating set or it has a neighbor in the dominating set, or both. Yeah, so exhaustive. So for all vertices in my graph, there is, so W, if W is a dominating set, if for all vertices in my graph there is a vertex in the dominating set such that V is equal to W or VW is an edge. So that's a dominating set. It's one of the classic graph problems which exist, have been studied for a long time. And so this is NP complete, but I'll show you now if the tree width is bounded, you can do this in some constant to the tree width times linear time if you have the 3D composition. So this is the the dominating set problem. So what we're trying to do is build a dynamic programming algorithm for this which exploits a 3D composition. If I have a dominating set in my entire graph, and my entire graph has this form that there is some separator, some graph below and some graph outside the separator. Now this is, suppose that this part is the graph which is associated to one of these nodes in your 3D composition. Now what I want, if I have a dominating set in my entire graph, then what should be the case? Well, all the vertices here should be dominated already. The vertices here can be dominated, but it might be that they still will be dominated from somebody which comes later. So actually, and then the vertices here also, so the vertices here can actually have basically 3 different states. Either they are in the dominating set, or if they're not in the dominating set, they can be already dominated, or they cannot yet be dominated. So these are my 3 states. If I have what I call a partial solution, which is a set of vertices which dominates everything except maybe a few vertices in the boundary. So this is what, this is what I call a partial solution, a set of vertices dominating all the vertices except maybe a few in the boundary. And this is what I call a partial solution, and the characteristic of a partial solution maps every vertex to the state either I'm in the dominating set, I'm dominated but not in the set, or I'm not dominated. Now, the main idea is that what I want to do is for every way of assigning a partial solution, I want the minimum size of a partial solution with that characteristic. So for every way, so for instance, if both V and W are in the dominating set, the minimum partial solution with this characteristic has size 3. I have V, W, and I need one of these 3 because I need to dominate this one yet. So 1, 2, and 3. So if I'm in the dominating set and this one is dominated, then the best solution is 2 because I take V and I take this vertex here. And so you have for all the 9 combinations, you have here. So, for instance, the red one is that this one is not in the dominating set and this one is dominated, then the best solution has size 1. I just take this vertex here. So you have a table, and the idea is that I want for every node in my tree decomposition, I want to compute this table here. You see this table has size basically 3 to the 3 width number of entries. Yeah, so this is the main idea of the algorithm, to compute these tables. Now, if I have the table for the root, I can just find the answer. Basically, I need to look at all the states which don't have a not dominated and take the minimum value there. And this is the root. Now, what I need to do is to show that for each of the 4 different types, I can compute a table if I have the table for the child. Yes? Now, for a leaf, it's trivial. I don't tell that, but for each of the 3 other types, you can look at this. So if I have an introduce, so I have one new vertex, and this new vertex has a for this new vertex has a V has only neighbors which are in the boundary of the previous one. So I have the table for the child, and now I want to compute the table for this introduce node. So for each of the 3, oh no, I didn't. Oh yeah, I was planning to draw a little bit of this on the whiteboard. There's a sheet. So basically, what you need to do is for each of these table entries, you need to look. For instance, let's say I want to do the not. I want to compute this. So I say V is in and W is not. Now, if W is not, then V cannot be in, because now you see actually that that this one vertex, if I put V in this set, then W cannot be not dominated, so I ignore that one. So I'll put an infinite there. If I put an EII, for instance, then they're both in. Then instead of looking what happens in this graph, I look up. So if W is in, I pay 2. And if V is in, I pay 1 more. So I add 1 and I add 3. And just by looking at this table and what happens in this back, you can just compute the next table. So this is for the introduce. For the forget, it's even simpler. It's kind of a projection of the different cases. You just take for each of the 3 cases of the forgotten vertex, you take the smallest one, and this gives you the value. The hard one is the join node. And the traditional algorithm uses 5 to the n algorithm, or actually if you don't look close to it, it's a 9, and we'll see later that you can actually improve on this. So suppose I have a join node with 2 children, say I is a join node with children j and j prime, so you glue these graphs together. Let's just quickly go to the picture again. This is the join node. I have a table for this one, I have a table for this one, and I need to make a table for that one. Now, basically what you can do is you can look for each table entry for this and for each table entry for that node, whether you can combine them, and if you combine them, what happens. Now, what happens if you combine them? First of all, the same vertices here and here should be in the dominating set. So if the vertex has state I, then it should have state I here also, otherwise you cannot combine these. Now, if a vertex is dominated here, if and only if it is at least dominated here or there. So that's what you will do. You see if you agree on states, and then you set the states of each vertex in this way. Its state is in if they're both in. The state is D if at least one of them is D, and the state is N otherwise. And then you take the best over all these. You update a table entry for the new state you get, and then you compute in this way. And because you don't have to, you only need to combine i's with i's here, so basically you have to, for every state you have to look at 5 combinations This gives you a 5 to the n algorithm, 5 to the 3 width algorithm. Yes? So this is how you compute a join node. So what I do now is for every node in my tree decomposition, I compute this table bottom up. So I start with leaves and then go up till I have the table for the root, and then I can read off the answer for the root. And this is the basic way how you do dominating set. It's an example which works for many other problems. In many cases it's much more complicated for dominating set. It really takes sometimes weeks just to write down how some of these algorithms to get all the technical details right. But the main idea is the same thing. And what is important is always you exploit that the only vertices which still can get new neighbors are the vertices in this border. This is the thing you always are exploiting in these dynamic programming algorithms. Are there questions at this point? So this is all. How do I do this? I'm always pressing the wrong button, sorry for that. Okay, thank you. I should press this one and not that one. So it works a lot. So the basic idea is you formulate what is a partial solution. You define some equivalent relation on partial solutions, but looking what happens at the boundary, and you want that this has a small number of equivalence classes as a function of the size of the border. And these equivalence classes should somehow tell that equivalent partial solutions can more or less be extended in the same way to a full solution. And then you show that each of the 4 types of nodes you can compute the table fast enough. This is the approach which you use. So we had the classic algorithm was 5 to the 3 width times linear. Then in 2002, Albert and Niedermeyer showed that you can have a trick and use 4 to the 3 width time. And then in 2009, together with Johan van Rooij and Peter Rosmanieth, we showed that you can actually do 3 to the 3 width time, but you pay a little bit more extra in the polynomial factor. Actually, a polynomial in the 3 width and 1 factor of n. It's a technique which works for many other problems, and I'll explain it here for dominating set, and I'll ignore all the polynomial factors because that's get messy at some point, and there are some tricks to get it even better by some technical ideas, so don't have time for that. Now, first of all, instead of computing the minimum dominating set, what I also can do is count the number of dominating sets of a certain type, of a certain size. If you just don't want to know, the minimum one, what you can do for each size of a partial solution, you with a certain state, you count the number of partial solutions with that state. And the same type of algorithm works also. Instead of taking minimas, you have to add numbers of partial solutions. This is the main difference. So I can also compute a number of them, and also, and then the whole thing goes on through. So basically, it costs you order and more because you have to, for each number, you have to of each size, you have to do these things. And then actually, it costs even bit more than order n work because you work with n-bit numbers. So that gives you another additional polynomial factor. But now the idea is that we might want to work with different states, and we introduce now a new state, which is a strange one. It's a question mark, and the question mark, if I count the number of solutions, I can do this. So I say a question mark state is, if a vertex has state question mark, I say it's not in the set, but I don't know if it's dominated or not. So for instance, if I have I and the question mark, then the minimum size here is so V is in the dominating set, W is not in the dominating set. The minimum size of a dominating set of this type is, well, you still need one vertex here, so it's 2, whether W is dominated or not. what I'm going to do is for each of these states, I'm going to compute for each triple, which is a value, a state, and a size, I'm going to compute the number of these partial solutions with that state. So now I can in this way get two types of tables. I can have the tables which are the classic ones, so with the classic triple of states. So the integers, I'm in the set, I'm dominated, or I'm not in the dominating set. This gives me a table where NHQ is the number of partial solutions with state H and of size Q. But I can also have, for a state assignment, which maps every state to in the dominating set, I don't know, and not in the dominating set, and a size Q, I can compute the number of partial solutions with that type of state and size Q. So I have two tables, and the interesting idea is that the fact is that if I look to the number of partial solutions, then these two tables really give the same information. Namely, if you have one of these tables, you can transform this table to the other one in basically 3 to the power the size of the set time. 3 to the border set size time. And so this is actually convolution in disguise. So it's just convolution. But what can you do is what I do is I just, for every vertex or coordinate in a table, I just basically change the states for that table. So first I have, as if I have 3 vertices, VW at X, then first, suppose I want to go from a table which has states I, D, and not, and I want to go to, so they all have either states I, D, and M. Then the first thing is I'll make a table where the first vertex has an I question mark N, and the others still have the old triple values, and then I do it for W, and then make a table where also I'll change this in a question mark, and then I'll change that in a question mark. To go from one table to the next, what you just have to do is you know if you want to compute a question mark, you just have to look at the number of these and the number of n's, and the other coordinates are the same, and then you add them up. And in the other way back, you know that the number of these is just question mark minus n, or n is question mark minus d. So you can just look at these values and just subtract or add and get the same values. I hope this was not too fast, but the idea is that this helps to speed it up. So, well, the point is that if we look to dominating set, then the integers cost basically 3 to the 3 with time. The integers, the forget also costed 3 to the 3 with time, but the join was more expensive. So what I can do is for a integers and a join node, I just use the tables as I was using that. But if I want to do a join node, what I do is I first transform my tables to a table with the new base, with the question marks. Then I can combine these tables with question marks fastly, and I'll come to that, how you do this next in my next sheet, how I can combine them. And then I have a table with the new values, and I transform it back to the old values again. And because I count the number of solutions, I can do this quickly. So how do I'm going to combine these tables for join nodes? Well, the nice thing is that actually, if I want to, if I have in my, so I have this I have this join node where I join basically two things together. Then if I have a question mark in the final result, I should have a question mark in the first case and a question mark in the second case. So I just can add the similar, I just can add the values of the children. Actually, to be very precisely, there are little nasty details because there is actually a correction term and so on. But the main thing is I look at the number of solutions left and right, and I just have to multiply these. And then this is more or less how it goes. So, so the intuition is that the question mark left and the question mark right combines to a question mark together, because if you are in the one subgraph and the other subgraph not dominated, you're dominated here, and not, or if you don't know and you don't know, you don't know, and if you are not dominated left and not dominated right, you're not dominated here. So in this way, my combination goes quickly, and I actually have a 3 to 3 width time algorithm for this join node here. So the technique works for many problems. This is, I gave here as an example the problem of dominating sets, but it works for many problems. Counting perfect matchings, many so-called sigma rho domination problems, which are generalizations of domination, and versions like independent dominating set, also many partition problems. And the nice thing is what we have is that actually the algorithm is more or less optimal, because if you look to the running time is a polynomial on n times the size of a table. And and this table, it seems that you have to compute it anyhow. So if you use the dynamic programming algorithm on graphs of bounded tree width, this is more or less what you expect. And actually, there has been a recent paper by some people, Fedor Fomin and others, I think. Fedor and others, who showed that actually for certain problems like dominating set, this is optimal. So 3 to 3 width is optimal for dominating set. For a number of other problems, they also show, assuming the exponential time hypothesis. In practical, well, if you look to real algorithms, you have this polynomial extra factor, which actually means that there are only few cases where it's actually faster for real world size graphs, but in theory it's really nice. And one of the other things is that also for convolutions you have this bad thing that worst case is best case is worst case. You really need to compute everything, instead of for normal dynamic programming there are often many entries which you don't need to compute. So this idea is used recently in recent work by Sihan et al., which I'll explain next in the cut and count technique. And the idea here is that I use randomization, combine this with this convolution, and get algorithms for problems like Hamiltonian Circuit. So in my explanation, I talked about counting the number of dominating sets of a certain size, and that directly gives you, of course, the minimum size dominating set also, because it's the minimum size where the number is 1, at least 1, and not 0. So in that sense, for decision problems, it works also nicely. So if you look to Hamiltonian Circuit and you try to do dynamic programming on it, these algorithms typically have running times of a constant to the 3 width square, or maybe if you're hard working, 3 widths to the log of the 3 widths for some constant. So that's well, we would like to have algorithms where the constant factor depending on tree width is of the form a constant to the power tree width. And this has really nice consequences. And this is in the cut and count technique, which I'll explain next. So as a running example, I use the Hamiltonian Circuit. You all know Hamiltonian Circuit? Yes? Okay, good. So there is a main loop around this, just a technicality, which I'll just fix some vertex, and then for every edge out of this vertex I test if there's a Hamiltonian circuit which uses this edge. You can do this differently, but so this costs you an order n time extra, because, or the degree of the vertex. You take a vertex of minimum degree and then run this for all these edges. And you know if there's a Hamiltonian circuit that at least one of them has a Hamiltonian circuit. Now for this edge I fix some direction. So I say, okay, V is before W. This is my first step. And now I'm going to try to test the Hamiltonian circuit of a Hamiltonian circuit which has this edge VW in this direction. Instead of, what I now do is, instead of computing Hamiltonian circuit, I'm going to compute cycle covers. So what's the cycle cover? A cycle cover in a graph is a set of directed edges such that every vertex has one incoming and one outgoing edge. Or it's also a two-factor, but it's directed, so you have basically, if every vertex has an edge in and out, then my whole graph looks like a number of disjoint cycles, right? And I have one additional condition. I want that the cycle cover contains this edge VW in the direction, in the right direction. So somewhere I have VW. So my Hamiltonian circuit is one example of this, but there can be many more. Well, one of the other things we note and which we'll exploit is that if I have a cycle cover which is not a Hamiltonian circuit, then this guy has a brother. Namely, I can take one of these cycles and reverse the direction. And this is also a solution. And so for every, I cannot do this with the Hamiltonian circuit itself, because then I would reverse the edge VW. So I take one of the copies which does not contain VW, and I can reverse the direction. So any cycle cover which is not a Hamiltonian circuit has basically an even number of copies. This is what we're going to exploit. So if the number of cycle covers containing VW is an odd number, then I know that my graph has a Hamiltonian circuit. But this is not enough, because I can have an even number of, if I would count the number of Hamiltonian circuit, of cycle covers containing a certain edge, and I see that this number is odd, then I know there's a Hamiltonian circuit. This is not enough, because I can have an even number of Hamiltonian circuits, and then I don't know anything still. So what I do instead is I use a weighted and randomized approach.
So the graph is undirected.
The graph itself is undirected.
Cycle cover is directed.
And the cycle cover, I count the number of directed cycle covers. Yes? So that's what I do. And now I want to know if this number is odd. But instead what I do is, for every edge in my graph, I randomly select a weight. So I give it weight 1, 2, up to, and the maximum weight is 2 times the number of edges. This is my random weight. Now, now what I am going to do is, for every value, in 1 to 2n times the edge, make a number of edges, so basically n times the maximum weight, I compute the number of cycle covers that contain this edge in this direction of that weight. Yeah, so I want the number of cycle covers of weight 1, the number of cycle covers of weight 2, and so on. To do this, I'll exploit the tree, I'll go and I compute these numbers using a tree decomposition of the graph. Now, if for at least one of these values this number is odd, then I know that there exists a cycle cover, and otherwise I return no. And the nice thing is actually that this algorithm has a probability of success of at least 1/2. So that was to explain that. There are 2 things to explain. There's the dynamic programming. Let's first go to show how you actually how the technique is for. So there is the famous isolation lemma. That is the following. I have a set family over a universe, and for every member of the set I choose a weight in 1 to the size of my universe. N is the size of my universe, uniformly and independently at random. I give it a weight. Then the probability that there is a unique set in this family of minimum weight is at least 1 minus the size of the universe diameter. N is just the value I choose myself. In this case, N would be, in my example, N is 2 times the number of edges, this number which I defined here, and U is the size of my universe. Now, in our case, U is the number of edges and N is 2 times the number of edges, so that means that 1 minus U divided by N is 1/2. Yeah. So what this means is, and my family is actually the family of Hamiltonian circuits. So the probability that there is a unique Hamiltonian circuit of minimum weight is at least 1/2. This is what this isolation lemma is doing here, telling me in our algorithm. Now, so N is a value I can set myself in the isolation lemma, and in our case I set N to 2 times the number of edges. Yes? Because, and you can make something larger, but then I do this because then this value is 1/2, and then I have a success of at least 1/2. So my family F is the set of Hamiltonian circuits using the edge VW in the right direction. And the probability that there is a unique one of minimum weight is at least 1/2. If there is a unique one of minimum weight, then the number of cycle covers using that weight is odd, because I only count this unique Hamiltonian cycle once, and all the cycle covers which use 2 or more cycles, I count an even number of times, so I have with probability at least 1/2 a unique one. An odd total number. And this means that my algorithm here, I'll have to press the right. This algorithm here returns, this loop here, this step here returns with probability 1/2 a correct, will return the answer 1/2 with probability at least 1/2 if there is a Hamiltonian circuit. And so you repeat it a number of times, as long as you can make the probability of success as high as you want, and otherwise you return no. If there is not a Hamiltonian circuit, then you know that you will always answer no, and if there is one, you will with high probability answer yes. Now the nice thing is that actually, why is this useful for graphs of bounded tree width in this setting? Because counting number of cycle covers is fast. You can do this in 4 to the tree width time by basically using an approach which is similar to the dominating set problem. Now in this case, for every vertex you have 4 partial solution, 4 states, whether it can already have its incoming edge or not, and it can already have its outgoing edge or not. So there are 4 possibilities for each vertex. So I have tables of 4 states, and then using the convolution trick you can actually make also the join node to work in 4 to the tree width time and get a 4 to the tree width time algorithm. So this is how you would compute the number of cycle covers. Yeah. So this was introduced by Sigan et al. And they use it for many problems. So Steiner Tree is a nice other example. Steiner Tree is a famous graph problem where you have a number of vertices and you have to connect them in the cheapest possible way. This actually has quite some applications in real life also. You can do also weighted versions but the weight should be in unary, so you cannot have arbitrary, you have to count the number of bits, you have to count, the weights should be bounded by a polynomial in the input size. Feedback vertex set is the problem that I have to remove as few vertices as possible to break all the cycles in my graph. This also works for directed versions, by the way. Connected vertex cover is you have, well, I don't explain a vertex cover, but it should be connected. Connected dominating set is that you ask in addition that the dominating sets form a connected subgraph. An interesting one is the so-called graph metric 3SP. Also again, my length, the weight should be polynomially bounded, so I ask for a circuit in my graph which visits every vertex at least once, but the total length should be as small as possible. So it's more or less DSP, but then inside a graph. And there are a number of corollaries. For instance, I think I mentioned them in my next slides. Yeah. Oh yeah, so connectivity problem. What's this? I think, oh yeah, here are the problems explained now. So, I thought that. So Steiner tree, I have a number of vertices, the red vertices, and I want to connect them in the cheapest way possible. So the yellow vertices are actually a solution here. And there's the 3 vertices, I need 3 vertices to connect the red ones. Connected vertex cover, let's go. Little feedback vertex set. Okay, so what I wanted to discuss is that actually there are some nice consequences for speeding up known results. People looked at parameterized algorithms where you try to solve these problems as fast as possible as a function of a parameter of the problem. So k is, say, the target value of your problem. So the previously fastest algorithm for connected vertex cover used 2 to the 4.88 k times a polynomial and n time, but using this you can basically have a randomized approach which uses 2 to the k time. So that's a connected feedback vertex set. Can also gives quite a dramatic improvement. 46 to the power the tree width to the target value, and now you can do it in polynomial in n times 3 to the target value time. Feedback vertex set improves from 3.8 to 3 to the target value. It also works for several problems on H-minor free graphs, and well, or on planar graphs. Now, many of these algorithms, basically what you know is that if your graph doesn't avoids a certain minor, then the tree width is bounded by the square root of the number of vertices, but also in several cases you know that some problems have a tree width which is bounded by a square root of the target value. So like dominating set on H-minor free graphs. And in this way you can get for these problems a running time of this type. So what I really like also are some improvements for small degree graphs. There is a result by Fomin which tells me that the tree width of a graph is bounded by 1 divided by 6 times the number of vertices of degree exactly 3 plus 1 divided by 3 times the number of vertices of degree 4 plus 1330 times the number of vertices divided by 5 plus the number of vertices which is bigger than 6, and then some small term which is actually, it should be actually, or it's epsilon n should be actually, the epsilon can be as small as you want if n goes to infinity. So now this has nice consequences. For instance, if you look to a Hamiltonian circuit of graphs of maximum degree 3 or 4, well, then we have an algorithm which uses 4 to the tree width time, and then if you would just plug this value in, so if the maximum degree is 4, for instance, then it's 1/3 then you would get something like 4 to the 1/3 n time, and that is much faster than the previous one known. So you get also these exact algorithms, basically improving on things that people like Knuth and Tarjan worked already on 40 years ago. They tried also having these algorithms, and here you see how you can actually use these techniques to get faster algorithms. Still, all of these algorithms, I should tell, are randomized, while many of the results they improve on are deterministic. There's an additional trick to speed up for maximum degree 3 graphs due to Björklund. So, it's good that I press always the wrong button, but so what I try to show you in this talk is tell a little bit about dynamic algorithm, programming algorithm through decompositions. So actually what I assumed is that you get this tree decomposition. Now if you only know that the tree decomposition, that the graph has tree with at most k, for some small k, then finding it is actually often the worst step. It takes much more time than running these algorithms on it. So that is really a problem too, which is standing there. But in many cases you also get it for free, like this result here by this foaming result. This is just a constructive proof which just gives you the tree decomposition. You can construct it, so you have it. And if you have other cases, you also have these constructive results, and then it works nicely. So I showed you two new techniques. One is this idea of using convolutions and changing the representation of your partial solutions to another one, such that you can do the join faster, and the cut and count technique, which uses this randomized approach, the isolation lemma, and just make sure that everything you count more than you want to, but everything you count too often you count an even number of times, so they all cancel each other in that way. Then our relation notions to tree widths, which are used branch width and rank width, and Sang-il knows much more about these than I do, but they are also quite cool and important. And we worked on for the convolutions. We have also a paper where we basically generalize this technique and show that also you can use this for getting faster algorithms on branch decompositions and rank decompositions. Or actually we use click width in that paper. So the convolution technique you can actually generalize, and so far, because the work is very new, people did not look yet at the cut and count technique for these related notions. So Johan told me that he believes that in several cases you can get further improvements on running times by using branch decomposition instead of tree decompositions. But Johan now works on a company, so here is a good plan for getting improvements. He will not work on it anymore. So this is one question, for instance, like Hamiltonian Circuit. Can you speed that up using branch decompositions instead of tree decompositions? So this is, and also say notions like click width or rank width that might be interesting to see whether what you can achieve by using the cut and count technique. Okay, so that was what I wanted to say. Thank you for listening.